Basically, I want to do a video on three-dimensional manifolds. Now, at the moment, I haven't really said enough in this course to prepare you for that. So what I want to do today is to introduce some more concepts to do with two-dimensional manifolds, like surfaces, which are going to help you to be able to make that next step up. But I don't just want you to think of this as a kind of drudgery learning kind of thing that you have to do in order to understand the more interesting concept of three-dimensional manifolds, which is a very interesting concept because it relates to things like the structure of the universe and lots of fantastic cosmological questions like that. But two-dimensional manifolds are pretty interesting as well. And I've already made quite a few videos about them. Basically what we're talking about here are surfaces which are bounded. So I've shown you some fairly simple ideas of these kind of things, like a sphere and a torus. And really today I'm going to stick with quite simple kinds of surfaces like spheres and toruses which have a handle. Maybe I'll also consider a torus which has two handles, kind of two-holed torus if you like, something like this. And I'll consider general torus with a general number of holes. So you might be wondering why I'm going to be going over old material again. And the reason, and it's an important thing, is that I'm now also going to consider a bit of geometry. How can I put it? Knowing about geometry can help you with topology because topology forces certain things to happen in geometry. So, if you have some kind of surface and you see that that surface is forcing a certain kind of thing to happen in geometry, then that tells you something topologically about that surface. So even if you don't give a damn about geometry, which would make you quite strange, still understanding about the topology of surfaces is very important for you if you're topologically minded. So then, what kind of geometry are we going to talk about? Well, basically, we're going to talk about one of the most interesting revolutions that's happened in human history, in my opinion. And that's the kind of change from Euclidean geometry, which was for about 2,000 years considered the kind of open and closed book on what geometry is, to non-Euclidean geometry. And this might be worrying you at this point. You might be thinking, oh my god, I don't know anything about tensors or non-Euclidean geometry, and I'm very, I'm worried I'm going to get sort of overloaded in this lecture. But don't worry, because I'm going to introduce these things in what I think is really the simplest possible way, which is basically good old-fashioned polygons. This is all we're really going to need to think about for quite a while. And thinking about polygons and how they fit together, I think is going to really help us to understand about something called curvature. What curvature is basically how a surface is curved. Is it curved inwards like that? Is it curved outwards like that? Is it saddle shaped? Whatever. Thinking about how you can tile a surface with polygons, and whether you can tile a surface with polygons, is something which is going to teach us a tremendous amount about curvature. And it turns out that once you understand how a surface is curved, you understand what kind of geometry there's going to be on that surface. Now, what do I mean by a geometry on a surface? I mean, surely all surfaces are in 3D space, and in 3D space we have our ordinary everyday geometry. Well, what I mean is that imagine if you were a little ant which was confined upon a particular surface, say a sphere. Then in a sense you have a kind of geometry, because you can kind of move around lines, and you can have points that you can think about and various different things. But obviously that type of ant geometry on a sphere is going to be quite different to the geometry which we experience when we're walking around on a flat piece of tarmac. I mean, one obvious difference is that the ant can continue in a single direction around the sphere and end up coming back to where they started from. You can't do that if you're walking around in the middle of a desert, say. This is absolutely, obvious stuff. On a plane, the fastest way from point A to point B is a straight line. So now let's look, that's a kind of geometric thing. And now let's think about the same situation on a sphere. Unfortunately, it's a kind of novelty size sphere, so it's a little difficult to manipulate, but let's try and think about the same kind of problem. Suppose that we've got a point, let's say here, and we've got some other point, I don't know, let's say way over here. Now, what's the shortest point? What's the shortest line between these 2 points here? Well, our straight edge isn't really that helpful, of course, because it's only ever going to be tangential to the thing. I mean, obviously we can kind of squash down our sphere or something silly like that and try and bend round our stick. But it turns out that the kind of standard answer to this question is that this sphere has something called great circles. What's a great circle? A great circle of a sphere is a circle centered in the middle of the sphere which has the same diameter as the sphere. So if I try to give you an example, imagine this apple is a sphere, and I slice it. If I slice it right through the middle, then the kind of circle that knife will make with the outside of the apple will form a great circle. And all kinds of great circles can be produced in that kind of way. So essentially, a great circle is like one of the biggest circles that you can draw on the surface of a sphere. And it turns out that these great circles, I mean the equator is an example on Earth, these great circles are incredibly important for example, aircraft, because the shortest distance from one point to another is always along a great circle. And if you think about that, in Euclidean geometry, in normal geometry, the kind of analogue of a line is just a line, the ordinary kind of thing. But in a what's called a spherical geometry on the surface of a sphere, the important thing are these great circles, and they end up essentially substituting for lines. And if you think that through long enough, you basically think that there's actually a whole kind of new geometry on the sphere, where you think of great circles as lines and points as points, and you get slightly different answers to various different geometric questions. For example, on the plane, the angles of a triangle always add up to 180 degrees, but that's not the case on a sphere. Maybe I can just prove it to you quickly. It's not really what this talk's supposed to be about, but if I can do a fast enough demonstration, it's okay. So here's an example of a triangle which doesn't satisfy that on a sphere. So if we go straight down from the North Pole all the way to the equator, and then we turn 90 degrees and we go a quarter of the way around this great circle, and then we go back up to the North Pole. That's a triangle and all of its angles are 90 degrees. So that's not like a planar triangle at all. Okay, so to get a clearer idea of what curvature is, we've got to think about another idea which is called the tangent plane. And it's not exactly rocket science. The basic idea is that if you've got some surface and you've got some point on that surface, maybe there's points here, then you can imagine a plane which touches that point and which is tangent to its surface. In other words, it just kind of kisses the surface. Now you can see that this sphere is sort of curving away from this tangent plane. I mean, it's a bit big, but it's if we go this way, you can see that eventually the surface kind of curves away and its tangent plane ends up facing kind of towards me, whereas this static tangent plane here is still pointing this way. So because and also this happens in every direction, so if we also look upwards, we see that again this sphere, if we trace it away, it curves away from the tangent plane. And that's why we say that this surface here has positive curvature. The plane has negative curvature, because if we draw a tangent plane and we move away from it in any direction, we're not really, we're always sort of on the tangent plane, we're never leaving it in a particular direction. Okay, so that should tell you perhaps why this sphere has positive curvature. So spherical geometry is on spheres, and spheres have positive curvature. Hyperbolic geometry is on surfaces with negative curvature. So what is negative curvature? Well, the simplest exhibition of it is on a saddle. You know, just like you'd ride a horse on. And a saddle has negative curvature. What is negative curvature? Negative curvature is where if you pick a point and then you take the tangent plane at that point, then if you move away from that point, the surface can curve away in two different kind of ways, in two different directions away from that tangent plane. So let's suppose that we pick a point on the middle of this saddle. Now maybe you can just use your imaginations here. Imagine the tangent plane at this point. In fact, just to make it a little bit easier, maybe a bit of money might help, it usually does. There we are. So here's a kind of beginning of our tangent plane. Now notice that if we move away in this direction, we're curving away from a tangent plane downwards, if you like, and the same going back. However, if we move away from a tangent plane to the right or to the left, then the surface is curving away from a tangent plane in a different way, and that means that this has negative curvature. Let me give you another more mathematically important. Excuse me. Oh, lucky three. Let me give you another example of a surface which has negative curvature, and this one's really kind of important as far as historical things goes. It's a poor 3D printer's approximation of something called a pseudosphere. So the pseudosphere for hyperbolic or negatively curved geometry is just like the kind of sphere for spherical geometry and positively curved things. So can we see that this surface here is negatively curved? Well, let's have a go. Well, there's a point, and if you look carefully, if you imagine a sort of plane, a tangent plane at that point, then if you go up or down, you're sort of curving away from that tangent plane kind of this way or this way. So if you're sort of curving above the tangent plane, and if you go orthogonal to that, if you go around this this little witch's hat or whatever it's supposed to be, then you're kind of curving below the tangent plane. And so this is sort of similar to a saddle, and it's a surface of negative curvature. In fact, just for the sake of trivia, this is the pseudosphere is actually a massive deal in the development of non-Euclidean geometry. And the true pseudosphere is like infinitely long, and it kind of looks like this, but you never get to the end of it. And it was hugely influential in the introduction of non-Euclidean geometry, because suddenly with the pseudosphere, which is a surface of constant negative curvature, mathematicians actually had a physical model of non-Euclidean geometry, rather than just some sort of pie-in-the-sky notions. Okay, so we're going to talk about some regular polygons. Really simple stuff. Squares, pentagons, hexagons, septagons, which are seven-sided regular polygons. We're going to think about them, and we're going to think about how we can tile with them. And my claim is that if we know what kinds of regular tilings, that means when you put the polygons down and they all fit together perfectly over the surface, if we know what kind of regular tilings a surface has, that's going to teach something about its curvature and its topology. Okay, so here are our three regular tilings of the plane. The triangular tiling, the square tiling, and the hexagonal tiling. Each of these tilings fills two-dimensional space with regular polygons which all look the same in every possible sense. The vertices look the same, the edges look the same, the middle of the faces look the same, etc. If you extend out these patterns far enough. Okay then, so are these the only possible kind of regular tilings of the plane in this sense? Well, the answer is yes, but it's not immediately obvious, and I'm hoping that later on I will actually be able to prove this to you. It turns out that there's a fantastic result called Euler's theorem, which is actually pretty simple, and a lot of people think of it as one of the most beautiful ideas in mathematics. And using Euler's theorem, I can convince you of this fact pretty quickly. But I'm not going to do that today because there's other things on the agenda. So instead of giving you a proof, I'm going to do a little bit of experimentation and hand waving to try to convince you that something like this might be true. So for a start, why don't we try and do a tiling with, instead of using hexagons, which are six-sided regular polygons, why not try using pentagons, regular pentagons? So let's give this a go. Can we tile the plane with regular pentagons? I'm hoping this is on camera. Well, they must be touching face by face, and you see already we're encountering a kind of problem because they're not fitting together properly, and there's a space here but it's not big enough for us to fit another pentagon in. So I think already it's quite clear that we're not going to be able to kind of tessellate this space with pentagons. No, there's going to be holes. Okay, so why? Why are hexagons okay and pentagons are not okay? And are pentagons just rubbish? Well, no, obviously they're not. And one thing they have use for is for spheres. So if we want to do these kind of regular tilings on spheres, it turns out that pentagons are very useful. What we're going to try and do now, is fit these pentagons together, but we've just seen that we can't fit them together properly if they're all on the plane. So let's not let them be all on the plane. Let's try to pick them up a little bit. What I'm trying to show you here is that if we allow this surface that we're building to have a bit of curvature, then just maybe we can actually do what we want to do. In fact, we want to have 3 pentagons meeting at every point with no gaps on the edges. So there's going to have to be quite a lot of curvature here. Well, I think I'll probably stop there. Hopefully you can see that if we allow our pentagons to have some curvature, as if they were, say, on the sphere or something, then it is possible to stick them together. That doesn't necessarily mean that you can do a regular tessellation of a sphere using pentagons, but you can, and if you know much about Greek geometry, then you should know that, because there is something called the dodecahedron. Here is a dodecahedron. Oh, okay, this is confusing. This is actually 3 dodecahedra, one inside the other. It's something fancy which I made with my 3D printer, but if you can sort of avoid the distractions, just think about the outer dodecahedra. What is it? Well, essentially it's tiled by pentagons, and they're sort of the same in every way. So this is an example of a so-called platonic solid. And what a platonic solid basically is it's a tiling of the sphere with these totally regular polygons. Now, there are other platonic solids. There's 5 of them in total. So there's the tetrahedron, the cube, the octahedron, dodecahedron, and the icosahedron. And the polygons included in those are the triangles on tetrahedra, squares on cubes, triangles on octahedra, pentagons on dodecahedra, and triangles again on icosahedra. So it's kind of interesting again that when we ask this fairly normal question about how many tessellations there are about something like, well, a sphere in this case, we just get a fixed number, 5. There's only 5. So the tilings, the regular tessellations on the plane, don't work on the sphere. And the sphere is obviously topologically different to the plane. Just like the circle is topologically different to a line. But does this then imply, I mean, we've got an example of it, but is it true in general then that if 2 surfaces have different tilings, then they have to be topologically different? Well, we can see examples where topologically different surfaces still admit the same tilings. So, an example is our good old friend, the torus. Torus to the rescue. So here's our torus, and it turns out that the torus admits many of the tilings that the sphere does. And in fact, this is actually a consequence of the fact that in some sense the torus has a kind of total curvature of 0. Now, I should be very careful when I talk about things like total curvature or curvature, because there are many different types of curvature. But I'm not going to go into the details. Anyway, let me show you some tilings of the torus which will seem familiar to you, because you'll have seen them before on the plane. Here is one. This is the tiling of a plane with squares. So how do we make this regular tiling of a plane into a regular tiling of a torus? Well, it's actually just really easy. We just wrap this thing up like a torus. So as usual, we twist it up into a tube. We apply some kind of adhesive. And then we just twist this tube round and bring together the ends. Maybe we can tuck one inside the other. Oh, whatever, I'll just wrap it round there. So there we have it. It's a little bit lacking in volume, but it's a torus and it's tiled with squares. Now if you think about it a little bit, and if you read about toruses and their relations to things like video games and things, you'll see that there's actually a great connection between tori and sort of repeating sequences of rectangular things. For example, if you imagine you're a guy walking around in some strange world, and every time you step forwards, say a mile, you encounter a farm which looked identical to the farm that you're in before. And this happens if you also go in right angles. then it could well be that you're on a torus. Okay? Right, so anyway, what about our other tiling of a plane? Well, let's just talk about the hexagonal tiling. Does this also have an analogue on the torus? Well, yes it does, and here it is. This is something I 3D printed a while ago. Actually, if you look carefully, there are some small imperfections with this, but you could create it perfectly, and it would be a kind of hexagonal tiling of the torus. Okay, so I want to keep these videos short, so I think I'll take a little break now, and let me just leave you with where we are so far. Basically, my objective is to show you that there is a bridge between the kinds of geometry which can be induced on surfaces and the topology of those surfaces. And some component of this bridge has to do with ideas like curvature. And so far, I've talked a little bit about planar geometry, and I've talked about a certain aspect of planar geometry, which is what kinds of regular tilings you can do of the plane. And I've shown you that those are different to the kinds of tilings that you can do on spheres. And I'm sort of trying to convince you that for some different topological surfaces, different tilings are possible. And this is a kind of symptom of a different kind of geometry which naturally lives inside these different surfaces. So far I've just talked about spherical geometry and planar geometry, which is the usual one. And I want to move on to hyperbolic geometry. So I'll see you next time.